Hello ladies and gentlemen, welcome back to another video. Today we're going to be talking about how to find all of the factors and therefore find the roots of a polynomial. Okay, so that's kind of going to be what we're talking about today. And we're actually going to be talking about a lot of big concepts, but then kind of look at how we can apply those concepts when we're looking at a polynomial in terms of factoring it all the way. That's kind of our major goal, okay? The first concept we're going to talk about is something called the fundamental theorem of algebra, okay? This obviously is something very important. It's called the fundamental theorem, a really important theorem. And it was actually found by a German mathematician of the name Karl Gauss. Okay, Karl Gauss, who, if you ever want to look him up, he's considered one of the fathers of algebra. A lot of stuff that we do throughout the year came from him. Okay, in fact, later in the year, we'll talk about something called Gaussian elimination, also from him. But the fundamental theorem of algebra, what it states is that if you have a polynomial of degree n, and having to be greater than 0, right, so our normal polynomial definition, then you know that that polynomial will have at least one complex root. Okay. Now, it doesn't have to be one root in the complex number system. It doesn't have to be complex. It can be real, but it has to have at least one root. Basically, every polynomial has at least one root. So when we're trying to find roots of a polynomial, we know we're looking for at least one thing. Okay, at least every polynomial has at least one root. That also ties into what we call the linear factorization theorem. Basically, if you have a polynomial that has degree n, it will have n factors. Okay. So what that would look like is if you have a polynomial, we could rewrite a polynomial as a times x minus, we'll call it c1, okay, times x minus c2, on and on and on and on, until we get to x minus cn, where n would be the degree of this polynomial, okay, to have n factors, okay? So if I have an x to the fourth polynomial, that's the degree of my polynomial, I know there will be 4 factors, okay? Whatever your number is, you can have that many factors. That's how many factors it have. If it was x to the 5th, I'd have 5 factors. X to the 100th, 100 factors, so on and so forth, okay? Whatever the degree of your polynomial is, that is how many linear factors that can make up that polynomial. All right. Now, how does that work with the last theorem? You have to have at least one root. Well, Mr. Guy, wouldn't that mean we have n roots every time? Not necessarily. Remember, you can have a root that repeats, okay? I could have something that's x to the 4th, and my 4 factors are all x minus 2, all right? X minus 2 times x minus 2 times x minus 2 times x minus 2, right? That would be a polynomial made up of 4 factors. Okay, except that the only root I would have for that one would be 2, all right? So polynomial, if it's degree n, will have n factors, and it has to have at least one root. Could have more, it could have up to n roots, but it can only have, it must have at least one root, okay? What does that mean for us? Well, we're going to start seeing how we're going to kind of take that information and use it to factor a polynomial, okay? The last thing we're going to need to do that is what's called the rational zero test. Basically, it's a way for us to use a remainder theorem from the other day, but use it a little bit more targeted, okay? Basically, if a polynomial has integer coefficients, every rational zero of f will have the following form. The form will be p over q. Okay, so what those p's and q's are, the p's are factors of the constant term of your polynomial. The q's are factors of the leading coefficient of your polynomial, okay? So you're going to find all the possible factors of your constant term, all the possible factors of your leading coefficients, and any of those ratios could be a factor, could be a root of your polynomial, a rational root, okay? Only the rational roots will have that, okay? You could have irrational roots, you could have complex roots. Those will not show up, obviously, through this method, but this will find all of the rational roots, all right? So what we're going to do is we're going to combine this rational zero test. We're going to use our factor theorem we just talked about. We're going to use our fundamental theorem of algebra in order to fully factor these polynomials. So here, example is a polynomial. I want to fully factor this. Based off my factor theorem, I know there's going to be 4 factors I can write out, and I'm going to have up to 4 roots, but at least one root that I can find, okay? I want to find the rational roots that are there so I can start factoring this. The way I can find that, again, is by finding my p's and my q's. these are my p's, these are my q's. I'm going to find factors of the leading coefficient, and I'm going to find factors of this back here. Now, you need to include the positive and the negative factors of these numbers. So, for example, my leading coefficient is 1. The possible factors of that are 1 and negative 1, right? 1 times 1 gives you 1, and negative 1 times negative 1 gives you 1, all right? For 6, I'm going to have 1. I'm going to have 2. I'm going to have 3. I'm going to have 6. And then I'm also going to have the negative versions of those. Negative 1, negative 2, negative 3, and negative 6, okay? And then what I'm going to do is I'm going to basically find different ratios of P over Q and then check to see if they give me a root of this polynomial. The way I'm going to determine if it's a root is by using the remainder theorem, the factor theorem from the other day. I'm going to take that answer I get, plug it into this, and see if I get out 0. So for example, one number that I could check would be taking 1 over 1, which would be 1. Okay, so that's the P, this factor of 1 over 1. Plug it in and see if that gives me a answer of 0. Okay, that gives me out 0. Okay, I keep doing that until I find one of them that works. Okay, so for example, I tried 1. So let me take my calculator and plug 1 in. I'm going to have 1 to the 4th minus 1 cubed plus 1 squared minus 3 times 1 minus 6. I got negative 8. That means that 1 is not one of the ones that's going to work for us. It will not get us the right answer, okay? Now, what might work is let's try the next one I would think of, which would be negative 1. Let's try negative 1 and see when I plug that in, right, so f of negative 1, when I plug that in, is that going to work? Okay, will that get me out 0? So when I plug in negative 1, let's see, we're going to have negative 1 to the 4th minus negative 1 cubed plus negative 1 squared minus 3 times negative 1 minus 6, and oh, lo and behold, I got 0 for that one. Negative 1 is a it is a root, it is a factor, okay? So negative 1 is a root that goes into this. I need to write the factor that goes along with negative 1. That factor would be x plus 1. That's the linear factor that goes along with that root, right? Think about it. If I said equal to 0, that's the root that would come out. So I'm going to be taking x plus 1 and factoring it out of this. And the way I'm going to do that is by doing synthetic division. I'm going to set up a synthetic division problem. I'll put negative 1 out here. I'll list my coefficients. 1, negative 1, 1, negative 3, and negative 6. And then I'll go ahead and do my synthetic division and see what comes out. Okay, so negative 1 times 1 is negative 1, which gives me negative 2, which gives me 2, which gives me 3, which gives me negative 3, which gives me negative 6, which gives me 6, and 0. So taking out this x plus 1, and I'm going to list these over here. Okay, these are I'll call this my factors, or my facts, okay? These are my factors. I'm going to list them over here. So taking out this x plus 1, I'll be left with a polynomial x cubed minus 2 x squared plus 3x minus 6. And I'm going to start this process all over again. I'm going to look for p's and q's that work here, okay, plugging them in and find one that works, all right? Again, you can find p's and q's from here. You can take the ones from up here because one of them, they have to work in this function. Plug them in and find one that gives you out 0. I'll give you guys a minute. Go ahead and try, see if you can find one that works, and we'll meet back together. Now, you may find a different one than I do, and your problem might look a little bit different from there. But go ahead and try to find one, and then we'll meet back together and see if we both found a P over Q that when we plug in gives us out 0. All right, ladies and gentlemen, I found 2. Okay, 2 was one that when I plugged it in, it gave me out 0. So I'm going to go ahead and set up my synthetic division problem again. Over here, we'll list x minus 2 as a factor. Again, we know that because if 2 gives us out 0, then x minus 2, that's the factor that goes with it. I'll put 2 over here. I'll list out 1, negative 2, 3, negative 6. And we'll go ahead and we'll do our synthetic division. Bring down the 1. 2 times 1 is 2. Negative 2 plus 2 is 0. 0, 3, 6, and 0. Okay, so I can write this out factored as x plus 1 times x minus 2 times x squared plus 3. Once we get to a point where we have a quadratic, we no longer need to do this method anymore, okay? In fact, for this one, there actually are no more rational roots, right? These are the only rational roots. We're now kind of at this point here, okay? So we can write this out using complex roots. However, it's not going to be, we're going to do it by other methods, all right? For this one, because it's x squared plus 3, I can extract my roots by setting it equal to 0. Okay, sorry I'm writing up here, but x plus 3 equals 0. I can solve that. I'm going to get that x squared equals negative 3, and that x equals plus or minus the square root of 3i. Okay, and there's my last two roots, and that's actually going to tell me my last two factors. If I want to fully factor this, I can write out f of x is going to equal x plus 1 times x minus 2 times x plus root 3i times x minus root 3i. And there we go. I've now fully factored this polynomial. Okay, I found all the rational roots. This also happened to be my real roots. And then I had two complex roots, but I was able to write out all of my factors. All right. New thing from today, just because it was a lot we just talked about. There's a lot to this kind of method. So I want to kind of review the new thing. You need to do your P's and Q's. Find your factors of that constant term. Find your factors of that leading coefficient. You're going to divide them. It's going to give you a lot of different numbers. It's a lot of numbers. At least one of them for these problems will, when you plug it in, give you out 0. Okay, you need to keep plugging in until you find one that gives you 0. So I tried 1 and negative 1. Negative 1 happened to work. I could have tried 2, negative 2, 3, negative 3. All of these p-values divided by q-values until I find one that works. Synthetically divide that number out. Then, if you're at a quadratic, you can use our quadratic methods to find your last two roots to write out your factors. If you're not at a quadratic, do your P's and Q's again. Plug them in until you find one that works. I found 2 that worked. I did it again. I got 0 as my remainder, as I should, and I got x squared plus 3. That's a quadratic, so I then went ahead. I could either factor that. This one didn't factor. In fact, this one had imaginary roots. I found those imaginary roots, used that to write my two complex factors here, okay, that had the complex roots. All right? Fully factoring this polynomial. That's how we're going to do it, by applying this rational zero test. All right? Just remember your P's and Q's, everybody. Thank you for watching.